All right, good morning and welcome back. So we are going to start shortly. In the last team, we had to scrap the last team because of power interruption in our locality here. In any case, we are going to start from the beginning, and just as usual, whenever if you have any query during the class, feel free to post them on the live chat. I shall be definitely answering your queries. All right. All right. So when we introduced Laplace transform, we introduced Laplace transform as an extension or rather a modification of Fourier transform. And this modification allowed us to calculate the so-called Fourier transform for functions for which usually the Fourier transform wouldn't exist. And we said that Laplace transform of a signal xt, Laplace transform of a signal xt, we proved that can be defined as the Fourier transform of the same signal multiplied with a certain exponential factor. And I said this sigma was a suitable real number. Sigma is a suitable real number, right? And I'm going to explain what I mean by that. Okay, right? I'm going to explain that in this class as well. And so this is how we actually introduced Laplace transform to you. This was an extension made by Laplace over Fourier transform, and it was found that Fourier transform, you don't have a Fourier transform expression for many signals that cannot be absolutely integrated, right? So if you don't have a finite area under a function or a signal, you don't really have a Fourier transform, converging Fourier transform. You kind of have certain hacks, but you don't really have a converging Fourier transform for that, right? So Laplace created something called a decaying factor, or some sort of a factor that allowed Laplace to actually take Fourier transform for signals that were not originally possible, and that is known as the Laplace transform, right? So this is how we defined it, right? And our standard nomenclature, standard definition is this one. We define Laplace transform of a signal xt as this one: integration from minus infinity to plus infinity, xt multiplied by e to the power minus st dt, and this s actually has this minus sigma minus j omega. So basically this is minus s, and that's actually minus sigma minus j omega, right? So you have that, and this is called the bilateral Laplace transform. So you people already are familiar with the nomenclature, right? This is called bilateral Laplace transform. All right. So you people already know that, right? All right. Again, there are a few standard notation. So if I calculate the Laplace transform of xt and its xs, so we often use this notation. Just like Fourier transform, this notation actually denotes that xs is the Laplace transform of xt and xt is the inverse Laplace transform of xs. Also, there is another notation. So this is one possible notation. There is another possible notation where we say the Laplace transform of xt is xs. So these are all standard notations, right? So you can use any of the notations interchangeably without any issue. All right. So we said that. All right. And today we're going to look into certain, certain internal implications. In the last class, I mentioned this term, that sigma is a suitable real number, quite often while we derived the definition of Laplace transform from Fourier transform, right? So we actually used this definition quite a few times, and I promised that I would explain this, right? And also for deriving a few things, we kind of, with some assumptions, considered some limits to be zero and something like that, and we are going to explain the conditions under which those limits are actually zero. We are going to explain under which we are going to explain the conditions under which the limits are actually 0 or actually non-zero, things like that. So we're going to explain those terms today. All right. So let's start by calculating the Laplace transform of a few standard functions, and it has started raining. Okay, so I don't know how long, I don't know whether this stream is going to go well or not because it's raining, right? Anyway, so let's calculate the Laplace transform of our single most favorite function, that's the Dirac delta or the unit impulse function. Delta t is the Dirac delta or unit impulse function, right? And unit impulse is one of the most significant functions or significant signals in signals and systems as well as control systems. Okay, right? So let's calculate the Laplace transform of that. And what is the Laplace transform? Very simple. So you just use the definition of Laplace transform. So we integrate delta t multiplied with e to the power minus st with respect to t from minus infinity to plus infinity. And with that integration, of course, the result is, of course, we are actually using one of the properties of impulse, this impulse function. One of the properties of impulse function is this one. Okay, so we know that one of the properties, so this is certain properties of impulse function. Let me just write it down. Properties of delta t, or rather certain properties of delta t. So not all the properties. Yeah, so one of the properties is that, of course, if you integrate the function from minus infinity to plus infinity, and that gives you 1. Actually, we proved all of this. Okay, and there is another property that if we do this integration, the answer is f0. Okay, there is another property which says if we do this integration, so delta at minus b f t dt, this would be 1 by mod a f b by a. And for property 2 and property 3, the condition, so property for this one to be true, for property 2 to be true, the only condition that this signal ft has to satisfy is that ft should be continuous at t equal to 0. And also for this one, the only condition that ft needs to satisfy is the continuity at t equal to b by a. So actually what I mean is that this value must exist. This value must exist, right? So the signal should be continuous at those 2 points. So essentially like that. All right. So these three are some useful properties of Dirac delta. So we are going to use the second property here. So if I take delta t, multiply it with any signal xt or ft, and integrate it from minus t with respect to t from minus infinity to plus infinity, then we get f0. So here f is this one, right? So ft is this one. So f0 would be e to the power minus st. So the result would be e to the power minus st, where t is a 0, right? Where t is 0. So essentially this one when t is equal to 0, right? And of course if I put t equal to 0, this is invariably equal to 1. So we just found that the that the Laplace transform of delta t, or that is the impulse function, is just equal to 1, right? So we have just seen that, right? So that's one of the very simple examples. But before, I think this is, I mean, obviously understood, right? This is not difficult to understand. But before I jump to the next example, I need to explain the term e to the power minus st properly to you, right? So look carefully that the definition of Laplace transform requires you to understand this one. So this was the definition. So minus infinity to infinity, we have xt multiplied with e to the power minus st dt. All right, and of course we have this e to the power minus st term. Where did it come from? It essentially came from the fact that we multiplied e to the power minus sigma t with xt and tried to calculate the Fourier transform of that, right? Because we defined Laplace transform as an extension of Fourier transform, and essentially we defined Laplace transform as a Fourier transform of any signal multiplied with e to the power minus sigma t, where sigma was a real number. So because of that we have s, right? Just like that. So essentially, so what this is, this s is defined as sigma plus j omega, right? So we defined that way. So this happened in the last discussion, right? So you can go to the Laplace transform part 1 and see the entire discussion there. So this is how we defined sigma, sigma was our complex frequency, right? Right. So we shall talk about this term carefully now, but this is not our concern right now. Our concern is e to the power minus st, right? So if this s is this, then what about e to the power, minus st? Notice that sigma itself is a real number, omega itself is a real number, right? So omega is the imaginary part of this complex number and sigma is the real part of the complex number. But the real part and the imaginary part themselves are just real numbers, right? But this entire thing combined is a complex number, right? So e to the power minus st is e to the power minus sigma plus j omega, right? And now this is equal to e to the power minus sigma multiplied by e to the power minus j omega, and that's obvious, right? So I can expand this becomes e to the power minus sigma minus j omega, and then I can use the product rule of exponentials, right? So that is how we have it. Now look carefully that we have e to the power minus j omega. This is a purely imaginary number, right? So again, e to the power, sorry, minus sigma t. Where did the t go? I would have this one, right? So this is going to be minus sigma t into, now e to the power minus j omega t is something like e to the power j theta, right? Where theta is minus omega t. So I can write, then now I can use the Euler's formula. Yes. So I can use the Euler's formula, and I can use the Euler's formula to write this as cos of minus omega t plus j sine of minus omega t. Obviously this is like e to the power j theta, where theta is minus omega t, right? So I can express this in this way. So I would have e to the power minus sigma t, and then I would have, of course, cos of minus theta is cos theta, so I have cos omega t, and sine of minus theta is minus sine theta, so I would have minus j sine omega t, right? So now this is a complex number but made up of sinusoids, but this is a real part, real number, right? And it has started raining. I shall hold on. All right, so look at this portion here. Okay, so this is, try to understand, this sigma is a real number, right? So this is like 1, 2, 3, 1.5, something like that. Okay, so this is either a positive exponential, so which basically rises as t increases, or it's possibly a negative exponential where it actually decays as t decreases, right? But what about this term, right? What about this term? This term, look very carefully. This term is essentially a sinusoid, right? Or rather a complex sinusoid. So this e to the power minus j omega t is nothing but a complex sinusoid, right? So this is nothing but a complex sinusoid. So what is the minimum value that cos omega t can attain? That's minus 1. What is the maximum value that this cos omega t can attain? That's again plus 1. What about sin omega t? The minimum value this sin omega t can attain is minus 1. The maximum value that sin omega t can attain is plus 1, right? So this is essentially a complex number that can vary from minus 1 minus j. So it can vary from minus 1 minus j1 to plus 1 plus j1, right? So the real part can only vary between plus 1 minus 1, and the imaginary part can also vary between plus 1 and minus 1, right? For this part, right? Right? So this is the change that can happen here. But what about this exponential, right? What about this exponential? So if I just look at the exponential, if I just want to draw it, look carefully what happens here is that, so this is t, right? And this is e to the power minus sigma t, right? If sigma is a positive, if sigma is a 0, then this is 1. So that's not a big concern here. Oh, hold on, huh? Hold on for a second. All right. So if sigma is 0, then this is 1 without any issue, right? So right. All right. So now if I plot this, of course, look carefully how it looks like. So if time starts from 0, as say for example for when time is negative, so this has a positive value. So now we are considering two possible scenarios, right? When sigma is positive, then of course as time goes on, this becomes smaller and smaller. So this e to the power this quantity becomes smaller and smaller, right? At t equal to 0, this is 1 no matter what. So this plot right, this plot looks like this one, right? So this is what happens when I have sigma to be greater than 0. So this one for sigma greater than 0, right? Something like that, right? All right. But what if sigma is, less than 0? Right? So this is t, and this is e to the power minus sigma t. What if sigma is less than 0? Of course, if sigma is less than 0, then of course when time is positive, then this is going to be positive because sigma is negative, and as time increases, as t increases, this will increase, this will keep on increasing, and as such this is going to be pretty large, right? But at t equal to 0, the value is nonetheless going to be 0. Sorry, at t equal to 0, the value is going to be 1, right? So again, this is 1 at this point, this is also 1 at this point, right? Right, and this is true when sigma is less than 0, right? So if you have any query, feel free to ask, right? So we call this a decaying exponential. So what we essentially have is a decaying exponential, right? And this is a rising exponential. Okay, so this is a rising exponential and it's a decaying exponential, right? So of course that's understood. So these are the two conditions under which these two scenarios take place, right? So this is sigma greater than 0 and this is sigma less than 0. All right. Hold on for a moment. So sorry for the interrupt, and here look carefully. So we're talking about decaying exponentials and rising exponentials. So we're talking about this portion of the signal, right? So this portion of the signal. So this portion of the signal, so this e to the power minus sigma t can either look like this one or look like this one. So it could be either of these two, depending on whether sigma is a positive real number or a negative real number. Of course, sigma cannot be 0 in our situation. Yeah, that is what we have done. We have split e to the power minus st using Euler's definition, right? In Euler's definition, it should be e to the power j theta that can be expanded this way. So that is what we have done, right? It has a real part, we just split the real part like that, right? Right. So now with that said, so what we essentially have is an exponentially increasing or exponentially rising or decaying factor multiplied with this portion of the signal, right? And now sigma cannot be 0. If you ask me, sigma cannot be 0, because if sigma is 0, then we are nothing but talking about Fourier transform, and whatever happens with Fourier transform would happen to the Laplace transform if I consider sigma to be 0, right? So Laplace transform and Fourier transform would become identical to each other, right? Same would become the same thing if sigma is equal to 0. No, we cannot. Someone is saying, if we can we expand e to the power minus sigma t? No, we cannot expand minus e to the power minus sigma t, because in Euler's definition, this was the definition, right? E to the power j theta. So it has to be a purely imaginary number, but s is not a purely imaginary number. S is a complex number, right? So with that said, this is the portion, right? So try to understand now. If I ask you that what is the upper bound and lower bound of this signal, okay, what is the upper bound and the lower bound of the signal, then the upper bound, that lower bound of the signal is pretty understood, that the lower bound of the signal has to be 0, right? So it cannot be less than 0 because it's a exponential, right? So when this is negative infinity, the whole thing is negative infinity, the result is 0, right? So this signal is bounded between, it can never reach 0 per se, bounded between 0 and infinity. So this signal is bounded between 0 and infinity. So essentially I can say e to the power minus sigma t always lies between minus infinity and, so always lies between 0 and infinity, right? So in a sense that this signal kind of can become unbounded, right? This portion can become unbounded, but this is always bounded between certain fixed values, right? In the complex plane, this is bounded between certain fixed value. If I draw the complex plane, say for example, this is like the complex plane, right? Then this signal is bounded between, I mean this portion, this purple one is bounded between these values, right? So if this is the complex plane we are talking about, then cos omega t minus j sin omega t is bounded between these. This is 1 plus 1j and this is minus 1 minus 1j. So this complex number is bounded within this. So the value of this complex portion, this number, this portion here in purple would be bounded between this. So this is the bound of this, and for this portion, for this e to the power minus sigma t, the value can be anywhere between 0 and plus infinity, right? So my point being that this portion, this real part here, e to the power minus sigma t, can go to positive infinity, can go to 0, okay, can become any of these depending on my choice of sigma, and we're going to see how that choice of sigma actually affects our end goal. So let's now calculate the Laplace transform of a very simple thing, the unit step function, and you will see why this thing actually matters. Okay, so now let's calculate the Laplace transform of our Heaviside theta function or the unit step function. So ut is the Heaviside theta function, Heaviside theta function. So that's the name used by physicists, and we call it the unit step function. All right, so what is the Laplace transform of this? Again, let's use the definition, right? So we are starting integrating from minus infinity to plus infinity, and we have ut multiplied by e to the power minus st, with we are integrating with respect to t, right? So now again, what is the unit step function? What does ut look like? Again, you people know that already. Ut looks like this one. All right. So that's my signal ut, right? So it has a value of 0 when t is less than 0, and at t equal to 0 it jumps to 1, and when t is greater than 0 the value of the signal is equal to 1, right? So if I split this integral into two possible limits, so I can integrate from minus infinity to 0 over ut e to the power minus st and dt. Hold on for a second. And then I can say, okay, with that, say plus integration from 0 to infinity. So we are just splitting the limit, okay, into two possible limits here. Yeah, right. And for this portion, this is 0, right? This is actually going to be equal to 0, because within these limits, when t is negative, ut is 0, and because of that it's 0, right? So only this one will exist, and this ut here within these limits would be equal to 1, right? So essentially this part of the integral is actually 0 to infinity. We have 1, we have e to the power minus st and dt, right? So the rain has stopped. Hold on. All right, so that's fine, right? Now, of course, let's integrate this, and here we will encounter the first issue, right? So when in your mathematics class, which is actually kind of overlooked. So if I do the integration here, of course, that's going to be one like that, minus 1 by s e to the power minus st, and the limits are from 0 to infinity. And of course, this minus 1 by s is a constant, so which can go outside of this, and we have e to the power minus st, lower limit 0, upper limit infinity. Now here is a problem. The problem is in this one. Look very carefully. Of course, if I put the lower limit, it's going to be e to the power 0, right? No issues there. But when I put the upper limit of t, which is positive infinity, I have a situation, right? Let's look at that. This integral is not a proper definite integral. The name of this kind of integrals where one of the limits is infinity is known as an improper. This is one kind of improper integral. And it should be treated as such, right? So it's an improper integral. It's not a proper definite integral. Okay, it's an improper integral because one of the limits are infinity. That one way integrals can be infinite, and if somehow within definite limits of the integral, if the function attains a discontinuity, then that also results into an improper integral. This is one kind of an improper integral, right? So you cannot just put the limits like that. So what you can do essentially, the proper technical way of handling this kind of situation is that we are going to consider the upper limit to be something like a finite quantity. So again, this is the mathematical way of dealing with this, right? Say we are considering the upper limit to be, say for example, what should I say? Upper limit to be, let's say p, right? Let's say delta. Well, let's write it in a proper way. Let's say, okay, fine. We are putting the upper limit, right? But upper limit is the limit for t, where t actually goes to infinity. So I'm writing this way. So let's write 1 by s, and let's write this: t tending to infinity, and we have e to the power minus st, and minus, then if I put 0 here, that's 1. So that's not an issue, right? So e to the power 0 would be, e to the power 0 would be 1. Again, if you encounter any issue, feel free to ask. Now we are kind of worried about this limit in this particular scenario. We are kind of worried about this one. Okay, what about this one? Because that one can be pretty tricky, because s is not a real number, it's a complex number, right? S is a complex number. So let's try to calculate the limit. So we are going to take a side turn here and try to figure out what it means to take a limit, real limit on a complex number, right? So we are now calculating. So we are going to come back to this, right? So notice, what should I notice? That we are calculating the real limit of a complex number like that. So it's a complex number. The whole thing is a complex number, right? And if I just expand this the way we just treated it earlier, right? So what is e to the power minus st? We just did expand this, right, moments ago. What is e to the power minus st? That's going to be e to the power minus sigma t multiplied by this whole thing. So if I now go back, so that's going to be this one for which we are calculating the limit. So this is going to be e to the power minus sigma t into cos omega t minus j sine omega t. All right. So now we are calculating the limits. But now when t goes to infinity, what happens to this portion? What happens to the portion of the signal that I represent in purple? Okay. So this one actually stays between these values, right? So this one actually stays between these values. So this is minus 1 plus j. This is 1 minus j, right? So this actually stays between these values. So what I say is, I mean, this is finite, right? So when t goes to infinity, I mean, whatever value of t you want to put here, this is always finite. This is always finite, right? Because this varies between -1 plus 1j and +1 plus 1j, -1 minus 1j and +1 plus 1. So that square, right, in the complex plane. So that actually varies with finite number. So this can never go to infinity, right? It can become 0, but it can never go become infinity at least, right? Right? Something like that. It cannot even become 0, I think, right? Anyway, the point is this can never become infinity, right? That's the point. It's always finite. But what about this quantity? What about this quantity? Question is, what about, I mean, what about this quantity? Right? What about this one? Now, this is e to the power minus sigma t. Keep in mind, sigma is a real number. It could be a positive real number, it could be a negative real number. But in any case, it's a real number, right? E to the power minus sigma t. Now, I'm saying t is infinity. T is going to infinity, right? T is going to plus infinity. Now, look at the expressions here. Look at the expressions here. When t goes to plus infinity, so plus infinity is in this direction, right? Plus infinity is in this direction, right? So when t goes to plus infinity, e to the power minus sigma t can either approach 0, so this is approaching 0, approaching 0, right? So under this condition, e to the power minus sigma t approaches 0 when t approaches infinity, right? And here when t approaches infinity, e to the power minus sigma t approaching infinity. Look carefully, right? So when sigma is negative, right? So this is going to be a positive exponential, right? So when sigma is negative, say -2, this is going to be e to the power 2t, right? And subsequently when t is positive infinity, that's going to be e to the power positive infinity. And that way this approaches positive infinity. But when sigma is a positive real number, like say -2, -3, something like that, say -2, then when t is positive infinity, I have e to the power minus infinity, right? And subsequently it approaches 0, right? It approaches 0. So with this, I can say this will approach 0, okay? This portion that I have represented in green will approach 0. Approach 0 means it will have a value of 0. It will have a limiting value of 0 if sigma is positive, right? So I'm calculating e to the power minus sigma t. When sigma is positive, say 2, say 3, then I would have something like e to the power minus 3t, and t is positive infinity. So I'm going to have e to the power negative infinity, right? So, and that way it's going to be 0, right? So I'm saying that this e to the power minus st, this portion has two parts multiplied with it. One is a finite complex number, another is a real number that approaches 0 if sigma is greater than 0, right? So I can now say that is our conclusion with this is that the limit that we are calculating, limit t tending to infinity e to the power minus st, this would be 0 if sigma is greater than 0, right? Yeah. But if sigma is less than 0, then this is not infinity. So look very carefully what happens if sigma is less than 0. If sigma is less than 0, then e to the power minus sigma t would be positive infinity. But this finite quantity that can vary from +1, -1, +1j, -1j, things like that, this will get multiplied with the positive infinity, and that way I would have positive real infinity, positive imaginary infinity. So essentially what happens, this becomes undefined, and this will be undefined if sigma is less than 0. So if sigma is less than 0, I would have a positive infinity multiplied with many different complex numbers, right? So the limit will not converge, right? In order to limit to converge, it will have to be converging to a finite value, right? That will not happen. But if this is 0, if this e to the power minus sigma t is 0, then 0 gets multiplied with a finite number resulting into a 0, right? So essentially what we are having here is that, let me erase this, let me define this as a cases situation. So this has two possible scenarios. One scenario is that this is going to have a value of 0, okay, this is going to have a value of 0 if sigma is greater than 0, and this will be undefined if sigma is less than 0, right? So let me know if you understand the limit here, right? So if again sigma is less than 0, then what happens? As t approaches infinity, e to the power minus sigma t becomes positive infinity, and that way in this limiting situation I have positive infinity multiplied with some random finite complex number, right, varying between -1 and +1 j, like that square, right? So that will be like positive infinity multiplied with possibly many different complex numbers, so it will not converge, okay? And subsequently the limit is not infinity but limit is undefined if sigma is a negative number here. But if sigma is a positive real number, then e to the power minus sigma t converges to a 0, and subsequently 0 gets multiplied with a finite number, result is also 0. So the limit is 0 if sigma is greater than 0. And this is one of the most important portions of this Laplace transform convergence. I don't understand your question. Someone is asking if you encounter with the second case. Okay, and that is the problem. That is the thing. Someone is asking, what if I encounter this situation? We won't encounter this situation. The point is, if you recall the definition of Laplace transform, in Laplace transform, we actually chose ourselves a function e to the power minus sigma t that I multiplied with the original signal so that the signal was absolutely integrable. This is the point here. I am allowed to choose this one and allowed to skip this one. I am kind of allowed to choose this one, right? Because it is entirely up to us what value of sigma we are going to choose. Because in the definition of Laplace transform, if you go back and recall what we said in the Laplace transform part 1, there we said that we are kind of allowed to choose the value of sigma. So we chose the function e to the power minus sigma t and chose it such a way that when I multiply e to the power minus sigma t with xt, that whole function was absolutely integrable, and as such it satisfied the necessary condition for the existence of a Fourier transform. So we are kind of choosing our function our own way, right? So that is why I mentioned this term, a suitable real number. Sigma has to be a suitable real number. Sigma will have to satisfy certain conditions, and this is the condition it has to satisfy for this particular example. Unless sigma is a positive real number, your Laplace transform won't converge. So essentially the Fourier transform won't converge, right? Fourier transform of e to the xt into e to the power minus sigma t won't converge. So unless sigma is a positive real number here, the Laplace transform won't exist, right? So let's go back. So here I'm saying that this is going to be minus 1 by s into 0 minus 1. Now I can say that this is 0 because we are assuming, so this limit we are considering to be 0 because we are assuming sigma to be greater than 0. So this limit is going to be 0 if sigma is greater than 0. Otherwise this limit is not going to exist, and as such the Laplace transform itself will not exist. Got it? Otherwise the limit will not exist, and as such the Laplace transform itself will not exist. And if it does happen this way, then the answer would simply be 1 by s. So you are quite familiar with the term that the Laplace transform of the unit step is 1 by s. But this is how it happens. We are inherently assuming that sigma is a positive real number. Otherwise the Laplace transform won't converge. So therefore we can say that the Laplace transform of the unit step function ut is equal to 1 by s if we assume sigma to be greater than 0, and this is undefined if we assume sigma to be less than 0. All right, so if we assume sigma to be greater than 0, then this is going to be defined and this is going to be 1 by s, and if you assume sigma to be less than 0, then this is going to be undefined. The Laplace transform is going to be undefined. But what is sigma? Sigma is the real part of s. So this is how we write it. So we write sigma is nothing but the real part of s, right? Real part of s. So that's how that's the notation, right? And omega is the imaginary part of s. So that's the notation, okay, in complex numbers. So we say real part of s is sigma and imaginary part of s is omega, like that. So that's the notation. So instead of writing sigma, so there is a better way in which we can write it. We instead should write this as, so this is going to be 1 by s if the real part of s is greater than 0. And what is the real part of s? That's just sigma, right? And this is going to be undefined if the real part of sigma is less than 0 or just otherwise. So the Laplace transform of ut is defined to be 1 by s if real part of s is greater than 0. Otherwise, yeah. So this is the suitable real number value for sigma. So the suitable real value for sigma here is any positive real number, right? Got it, right? Now, why am I telling this? Because there are certain things that you would need to understand, right, about this, right? So with that said, if I now ask you just the opposite question. Now what if I ask you just the opposite question? Okay, but now my question is, what is the inverse Laplace transform of 1 by s? So my question is, what is the inverse Laplace transform of 1 by s? So you already know that the Laplace transform of ut is 1 by s. So the inverse Laplace transform of 1 by s is going to be ut, right? Right? No, you will see why. Okay, if I just ask you what is the inverse Laplace transform of 1 by s, you cannot just go ahead and say this is ut. No, it's not like that, right? We will see why. This might seem so simple that, okay, you might be already familiar with saying that inverse Laplace transform of 1 by s is ut, right? You might be familiar with many numerical problems that you actually solved in your mathematics classes, right? But unfortunately, this is not really as simple as it might seem. This is actually wrong, right? So the inverse Laplace transform of 1, even if I ask you the question, the problem is not in the answer. Okay, if I ask you the question that what is the inverse Laplace transform of 1 by s, the problem is not in the answer. The problem itself is in the question, because the question itself is wrong. Why? Let me show you another example and the answer will be pretty clear there. Okay, let me calculate Laplace transform of another signal, something like IUT but slightly modified. So we are calculating the Laplace transform right now of u of minus t. That's a time reflected and amplitude reflected ut. Now, of course, you did time reflection, amplitude reflection, all this reflection, in your signals and systems classes, and I would hope that you recall any of this. But in case you don't, this is what the signal look like. This is what this signal would look like. Right, so this is the signal, minus u minus t. Okay, so there is an amplitude time reflection and there is an amplitude reflection after that. Okay, so that's gonna be minus 1. So again, so this has a value of 0 and this is time 0. So essentially the value of the signal is minus 1 when time is negative, and at time t equal to 0 the signal jumps up to 0, and when time is positive the value of the signal is 0. Right, so it's just like that. So you just time reflect ut and then you do an amplitude reflection, right? I hope you recall these things. So let's calculate the Laplace transform of this one. Okay, we can, right? Let's use the definition again. Let's use the definition, right? So let's do that. So we have minus u of minus t multiplied by e to the power minus st dt, right? And with that said, I can now split the limit from minus infinity to 0 on minus u minus t e to the power minus st dt and plus 0 to infinity minus u minus t e to the power minus st dt. We just split the limit into the negative values of t and the positive values of t, right? And now look carefully. When t is positive, here look at the plot. When t is positive, the value of, so this is minus u minus t. When t is positive, the value of minus u minus t is 0, right? The value of minus u minus t is 0 when t is positive, right? And as such, this is going to be 0 as long as t is negative and t is positive, and within this limit from 0 to infinity t is positive, and of course this value is 0, right? And only we are dealing with this limit, right? And within this limit, when t is negative, the value of the function, value of this function basically, the value of this function is minus 1, right? So that's going to be minus 1. So let's write down the limit. So that's going to be limit from minus infinity to 0, right? And we have minus 1 into e to the power minus st dt, like that. Alright, so now if I do the integration, of course, then again we have a minus sign, then we have a minus 1 by s, so the whole thing kind of becomes 1 by s, and we have e to the power minus st, and the limits are from minus infinity to 0, and I can again bring 1 by s outside, and with that I can put the upper limit here, right? What if I put the upper limit to be 0? So of course the limits are for t, right? So if I put t equal to 0, then I have e to the power 0, that's 1, right? No issue with the upper limit. What about the lower limit? If I do the put the lower limit, then I have to write down the limit symbol once again. So it's like limit t going to minus infinity on e to the power minus st. Now again we have to think about this particular limit. So let's go ahead and think about this particular limit. Let's notice. Okay, what am I going to notice? I am going to now notice the limit of e to the power minus st when t goes to negative infinity. So it's going to be e to the power minus st. All right. So when t goes to negative infinity, now look very carefully. Okay, again let me expand it. Okay, again that using that expansion. So this is going to be e to the power minus sigma t multiplied by cos omega t minus j sine omega t. All right. Now again, once again, this portion is a happy and nice function, right? I mean, this cannot go beyond certain fixed values, right? So this is finite once again. So once again, this is finite, right? So once again, this is finite. But question is, what about this one? What about this one? What about this one? Question is, what about this one? Right? Is this finite or infinite? Now time is approaching minus infinity. Time is approaching minus infinity, right? So we are going to look at the other side. Let's go back. Let's go back to the plot. Okay. So time is approaching minus infinity. So we are kind of looking in this direction. Here time is approaching minus infinity, right? Here also time is approaching minus infinity, right? So now I want e to the power minus sigma t to be 0 when time approaches minus infinity. Here, see, when sigma is greater than 0 and if time is minus infinity, okay, so what happens? When sigma is greater than 0, say plus 2, right? So I would have e to the power minus 2t, and when t is negative infinity, I would have e to the power plus infinity. So that way, when time approaches negative infinity, this has a value of infinity. So when time approaches negative infinity, this approaches infinity, right? Right? And here, for this one, for the second example, when time approaches negative infinity, this one approaches 0, right? This one approaches 0, simply because when sigma is less than 0, say sigma is minus 1, then I would have e to the power plus t here. And then when t is minus infinity, then I have e to the power minus infinity. With that said, when sigma is negative infinity, this function, the second example, okay, this rising exponential would actually go to a zero value, right? So e to the power minus sigma t will have a value of 0 if sigma is less than 0. So now we have to get this condition. Again, sigma is our own choice, right? No one is giving us, forcing sigma on us. So it's our choice. So I can make this. So basically what we have is, so this will approach 0 if sigma is a negative quantity, right? If sigma is a negative quantity, once again look very carefully, if sigma is a negative quantity, say sigma is -1, then I would essentially have sigma, so -1, so e to the power t, right? And when t is minus infinity, hold on. So when t is minus infinity, it becomes e to the power minus infinity. So that way it becomes 0, right? So it will approach 0 if sigma is less than 0. And of course this one is finite, so I would have a 0 multiplied with a finite complex number, so the whole thing will become 0. Also, as the other case goes, if sigma is greater than 0, then this is going to be plus infinity, and as such, plus infinity multiplied by a complex number, it won't be a finite quantity, right? So I can say that this e to the power minus st, so limit t tending to negative infinity, this can approach a 0 if sigma is less than 0, and this can approach, I mean this will be undefined if sigma is greater than 0, right? Just like that, and let's go back and consider the situation. So with that said, I can say this is 1 by s, and then I can say this is 1 by s and then 1 minus 0. But when at the moment I write 0 here, I am assuming, so if I write 0 here, I am assuming sigma to be less than 0. Otherwise this limit will not exist at all. So the answer is 1 by s under this assumption. Assumption is that sigma is less than 0. So therefore I can say the Laplace transform of minus u minus t is also 1 by s if sigma is negative and it is undefined otherwise. And of course, what is sigma less than 0? That's just real part of s less than 0, right? So what have we just seen? We have seen that we took two completely different functions, right? So first we calculated the Laplace transform of ut, right? The Laplace transform of ut, we calculated the Laplace transform of ut, and that was this function, this signal here, okay? And the Laplace transform of ut was 1 by s. And then we calculated the Laplace transform of minus u minus t. That's a completely different signal. For that also, we somehow managed to get the same Laplace transform, right? We somehow managed to get to the same Laplace transform, right? So these two signals have the same Laplace transform, but look very carefully, the conditions are different. The condition for which this Laplace transform exists is this one, that the real part should be negative. Real part of s should be negative. Then only this Laplace transform exists. And the Laplace transform for ut would exist if the real part of s is positive, right? The Laplace transform of ut exists and it is equal to 1 by s if the real part of s is greater than 0. And as such, the Laplace transform of minus u minus t is also 1 by s if the real part of s is considered to be negative. So now let's get back to the question that I asked you earlier. So this question itself was wrong, right? I said, what is the inverse Laplace transform of 1 by s? The question itself was wrong. Why was the question itself wrong? The question itself was wrong because I did not tell you whether I am assuming the real part of s to be positive or the real part of s to be negative. If I am assuming the real part of s to be positive, then I would get one answer, and if I am assuming the real part of s to be negative, then I am going to get another answer. So the proper question would be, would be something like this. So there are two possible proper questions. Say for example, I can ask you, what is the inverse Laplace transform? ILT stands for inverse Laplace transform of 1 by s if the real part of s is greater than 0. I can ask you this question. That's a valid question, and the valid answer is, so the answer would be ut. And also there is another valid question I can ask you, what is the inverse Laplace transform of 1 by s if the real part of s is less than 0. I can ask you this valid question once again, and the answer would be minus u minus t. These two are perfectly valid questions and perfectly valid answers. But if I just ask you what is the inverse Laplace transform of 1 by s, the question itself is wrong. So the next time someone asks you, maybe a teacher asks you in a viva or something, or an interview or something, what is the inverse Laplace transform of 1 by s, just tell them ask them back whether they are considering s to be positive, real part of s to be positive, or real part of s to be negative. Because that is how things work, and we shall see why this is important. This entire idea would be important while we discuss stability for the most part, because right, as far as unstable systems are concerned, Fourier transforms are not a good tool to analyze them. You cannot in a straightforward manner analyze unstable systems using Fourier transforms. Okay, so we shall see why these things are important, right? But for the most part, understand that there is something called a condition for convergence, right? So here, this condition that I have given here, for which this is the condition, right? Condition for which this actually converges. Also, the condition for which this diverges. The condition for which the signal. But thing is, I am kind of the person who used to do this kind of things. Okay, if your question is not exact, I would return your question with another question. Right, so there is a condition, right? Here. Also, let's look back at this one. Because why wouldn't you ask? Because try to see that both of these are perfectly valid answers. To make fun of the examiner, you can just even say minus. See, if someone asks you what is the Laplace transform of 1 by s, inverse Laplace transform of 1 by s, you can just say it's minus u minus t. And if I say, oh, what minus u minus t, you can just show them why this is so, right? And they will be so impressed upon you that you are going to get the job. Okay. All right, so with that said, so these conditions that I'm giving here are known as the region of convergence. The condition under which the Laplace transforms exist are known as the region of convergence. For that matter, the conditions under which the Laplace transform exist is known as the region of convergence. In short, it's called ROC of the region of convergence. That's it. Okay, So the point being, whenever you're talking about Laplace transform, and it's also not valid for Fourier transform, but for any other transform where the transform variable is a complex number, right? Fourier transform, omega is not a complex number itself, right? So under those scenarios, we have something called the region of convergence, right? So a condition under which the transform will converge and a condition under which the transform will not exist, essentially diverge, right? So as such, we say that the conditions under which the Laplace transform would exist, okay, and this will be also valid for other transforms, like namely the Z transform, essentially when you study discrete time signals and systems, also known as digital signal processing, you will see that, of course, region of convergence would be one of the inherent things in those, right? Okay, and the conditions under which the Laplace transform would exist is known as the region of convergence. So unless I tell you the region of convergence, then talking about the Laplace transform or inverse Laplace transform is meaningless, more or less. You get the point, right? With that said, now you might ask, okay, if I go through, I can show you a few books right about now. Okay, so hold on for a moment. I did not prepare for this. Just a moment. All right, so okay, here is a nice book on control systems. Okay, this is the book on control systems by Dorff and Bishop, right? By Dorff and Bishop. So this is a pretty famous book on control systems. Now, if you look into the Laplace transform part here, you will see they do not talk about region of convergence. In this book, they do not talk about region of convergence. So this is the book on control systems. This is the de facto standard book on control systems. This is the book by Ogata, right? And here, so again, book by Ogata. Here also, if you look at the chapter on Laplace transform, discussion on Laplace transform, you will see they do not consider the region of convergence. They do not talk about the region of convergence, right? But here is a book on signals and systems, right? Again, this is Oppenheim's book. Okay, Oppenheim signals and systems. So now, if you look at this one, you will see the authors are talking about region of convergence. Here is another one, signal systems by Rawat. Okay, here also they are talking about region of convergence of Laplace transform. Here is another one, signal systems by Phillips. Here also they are talking about the region of convergence of Laplace transform. So do you see the pattern? Okay, whenever people are talking about control system engineering, they do not seem to talk about the region of convergence. Okay, so whenever people are talking about Laplace transform in the context of control system engineering, they do not talk about region of convergence. Okay, and whenever people talk about Laplace transform in the context of signals and systems, they do indeed talk about region of convergence. What do you think? Do you know why? Would you know why? Okay, and you will see why shortly, and I'm going to tell you. Look back at these signals, right? Look back at this signal and this signal. So we have two possible results, right? So if the examiner, or if in real life, if you are asked what is the inverse Laplace transform of 1 by s, if that is asked, you possibly have two results, right? Depending on the region of convergence. If this is the region of convergence, if the region of convergence is real part greater than 0, then we have one Laplace transform, that's ut. And if the region of convergence is less than 0, then we have another result, minus u minus t, right? Now, but let's go back and look at those signals. What is ut? Ut is defined as a signal that has a value of 1, so value of 0 when t is less than 0, and a value of 1 when t is greater than equal to 0. So this signal has a value of 0 when t is less than 0. So this is a causal signal, right? So this is a causal signal. Alright? This is a causal signal. So what are causal signals? Causal signals are those signals for which the value of signal is 0 when t is less than 0. So this is a causal signal. And let's go to this one. What is the definition of minus u of minus t? That has a value of minus 1 when t is less than 0 and a value of 0 when t is greater than equal to 0. Now this is a non-causal signal. Again, why non-causal? Because causal signals are those signals for which the value of the signal should be 0 when t is less than 0. So this is a non-causal signal. So the point is that if someone asks you what is the inverse Laplace transform of 1 by s, then you have a causal answer and you have a non-causal answer. So this is a causal answer. So here this is a causal signal. So I'm saying non-causal answer, right? So, and this is a non-causal answer, right? Right? So depending on the region of convergence, the same Laplace transform can have different inverse Laplace transforms depending on whether you are considering the signal to be causal or non-causal, depending on whether or not you are assuming that it came from a causal signal or non-causal signal. But in control system, we said in earlier classes that all the signals that I'm going to talk about here are causal signals. We are going to talk about causal systems, causal signals. Everything is causal in our discussion, right? And we did that in our transfer function classes, right? On our discussion on transfer functions, we said we would only deal with causal signals for the most part. For the 95% of the portion of this course, we are going to talk about causal signals, right? So if I say, if I am only dealing with causal signals, okay, if I am only dealing with signals that have a value of 0 before time was t equal to 0, when t is negative if the value of the signal is 0, if I am dealing with those kind of signals only, then obviously the non-causal answer are by default eliminated, right? These do not exist in our scope. If in our scope we only have causal systems and causal signals, then by default, by definition, by the very scope of our course here, we are eliminating non-causal signals and non-causal answers like that. And as such, this is the answer that you by default see in any book on control systems, right? But if I am dealing with this subject as a generic signals and systems matter, so if I am dealing with as generic signals and systems, then I am also going to consider non-causal answers, okay, right? So, and because of that, this non-causal types of answers will appear in books written for signals and systems. But for control system, for the most part, I mean for the entirety, almost for the entirety, we only consider causal answers, the causal signals like that. And so by our very scope of the subject matter taught to undergraduate students, only the causal answers are taken, and as such, you can safely ignore the region of convergence, right? Because only under one of those you will get the causal answer, and under others you would get non-causal answers, right? So the region of convergence is kind of skipped because you are only considering causal answers, causal signals, right? Okay. And again, what are causal systems? Another definition of causal system is that a system for which the impulse response is a causal signal. What is a causal signal? A causal signal is a signal for which the value of the signal is 0 when t is negative, right? And again, why causal? Because for the most part, the systems we are going to talk about, okay, what is the definition of a causal system? For a causal system, we can calculate the output of the system by knowing the present and past inputs, right? We do not need to know what would happen to the system in the future, what input is going to appear in the future. We do not need to know, right? So those kind of systems are called causal systems. Causal came from the English term causality. What is causality? There is a cause and effect relationship between signals and systems. So the inputs are causes and the outputs are effects, right? So cause would happen first and then the effects, right? In that way, the causality, causal systems. For causal systems, the input needs to appear first, then only you can see the output. And as such, the output of the system can be calculated by knowing the present input and the past inputs, right? And not the past inputs. Right? But for a non-causal system, you would require the knowledge of future inputs as well, right? So something like that. And for a causal system, it can be shown that for a causal system, the impulse response is also causal. Impulse response signal is a causal signal, and with that, and also I told you earlier that if I excite a causal system with a causal signal, rather if the input to a causal system is also causal, then the output is also going to be causal. And for the 95% of the portion of this course, we are only going to deal with causal systems excited with causal inputs. So by definition, by the very scope of our subject, only the causal answer is taken. So you can kind of safely ignore the region of convergence. But because you are ignoring something, it doesn't mean that it actually disappears, right? It is still there. All right. So with that said, I think this is a rather elaborate discussion on why the region of convergence is important, right? And as such, we are going to use the definition of region of convergence to define stability of LTI-BIBO systems. We will see. All right. So with that said, let's take another example. Okay. Again, a causal example. So LT, Laplace transform of e to the power minus at ut. Now, if I did this for Fourier transform, I would have to assume A is positive. Otherwise, the Fourier transform won't exist. So just to recall, the Fourier transform of e to the power minus at would be 1 by j omega plus a under only one condition, under the condition that a was equal to 0, greater than 0. If a was less than 0, this Fourier transform won't exist. But the Laplace transform would exist even if a is positive. Even if a is positive, the Laplace transform would exist. We will see why. And of course, the condition and the reason the Laplace transform would still exist even if a is negative is simple, that we are allowed to choose the value of sigma, and accordingly we will choose a different sigma if a is positive and negative. Accordingly, we can make the Laplace transform converge. Okay. But keep in mind, the Fourier transform, not the Fourier transform e to the power minus at, the Fourier transform e to the power minus at ut, this one, right? All right. Okay, so Fourier transform of, just so that you have this discussion clear, this does not exist if a is less than 0. So that's a side note. All right. So let's use this definition, right? And let's use the definition here once again. So minus infinity to infinity, e to the power minus at ut dt. And of course, since there is let's split these limits. From minus infinity to 0, I have e to the power minus at ut dt plus. So 0 to infinity, e to the power minus at ut dt, right? All right. And of course, since ut has a value of 0, ut itself is a causal signal. Since ut has a value of 0 when t is negative, and of course within this limit, within this one, t is negative, so this is going to be 0 within this limit, right? When t is from minus infinity to plus 0 minus, so when t is negative, ut is 0, so this portion is 0. So we are only treating the right one, right? So integration from 0 to infinity, we have e to the power minus at ut dt, right? And of course within this limit, ut is 1, So I can say integration from 0 to infinity, ut is 1, so e to the power minus at into 1 in, okay, what did I just do? I managed to forget to write e to the power minus st. All right, hold on. That's the definition of Laplace transform, right? Hold on for a second. All right, so this is going to be 0 to infinity, and within that limit ut is 1, and this is going to be e to the power minus st dt, right? And of course we can combine these two. And again, just one more thing, keep in mind that a is a positive, a is a real number. Okay, just this is the thing, a is real, it's not a complex number or an imaginary number, it's a real number. Okay, just keep that in mind, and we will treat the imaginary condition. When a is imaginary, we will treat that as well. Okay, and with Laplace transform we can actually have conditions under which a is okay, let's forget that a could be a complex number as well. We will treat that directly. So I would have e to the power minus a plus s t dt, that integral, right? And if I do this, this becomes minus 1 by a plus s into e to the power minus a plus s t, and the limits are from 0 to infinity. Okay, and of course limits are for t, and I can take minus 1 by a plus s outside, minus 1 by a plus s, and with that said I have e to the power minus a plus s, lower limit 0, upper limit infinity. And again we are treating this as an improper integral. So treating this as an improper integral is the proper way of treating it, right? So with that said, now I have the upper limit and the lower limit. Okay, of course t here. All right, so of course this portion would be limit t tending to positive infinity over e to the power minus a plus s t, and for the other part I would have minus, and the lower limit is, of course, if I put t equal to 0, I get e to the power 0, which is 1. Now notice this one, I want to find the limit of this one, right? Now notice, just one more thing, I am considering a to be any complex number. I am considering a to be any complex number. Okay, could be anything essentially. Okay, so notice that this limit okay, so it is like e to the power st, but instead of s I have a plus s. So essentially this can be written like this. So look very carefully. Previous in the let's see, let's go back. Let me just copy paste one of the things that I did earlier, right? Let's copy paste. Now what am I copying? All right, I'm copying this condition, right? Let's see why I'm you will see why I'm copying that condition. Let's recall this. Look very carefully. We previously discovered that when t tends to infinity, okay, e to the power minus st will have a value of 0 if sigma is greater than 0. So what is sigma? The real part of the real part of S is greater than 0, and it will be undefined if the real part of S was less than 0. Alright, so we actually previously figured that out. When t tends to infinity, t tends to positive infinity, the limit of e to the power minus st would be 0 if the real part of S is greater than 0, and it will be undefined if the real part of S is negative. Now look at this one. Doesn't it look very familiar with this? Very similar? Doesn't it look very similar? So what about this one? So instead of S, we just have a plus S. And since a and s are both complex numbers, they can be added. And as such, this is nothing very different from the thing that we had moments ago, right? So we had this moments ago. And the one we are right now writing is not very different. So we can kind of say the whole same thing, right? I can consider this entire a plus s to be p. What if this entire a plus s to be p? If I consider this a plus s to be something like p, then I can say this is going to be 0 if the real part of p is greater than 0, and this is going to be undefined. So I'm considering this entire a plus s to be equal to p, and again a is a complex number, and of course real numbers are just a subset of complex numbers, right? You know that. And of course if the real part of p is less than 0, right? If a plus s is considered to be p. But what is p? That's a plus s, right? So let's write a plus s. Right, a plus s. So I think that's not an issue, right? That's not an issue, right? So I'm using this as a since we know that, right? So I think this is clearly understood, right? All right. So now let's go back to something very important. Say we have two complex numbers. I have z1, a complex number, which is x1 plus jy1, and z2, another complex number, which is x2 plus jy2. x1 is the real part of the first number, x2 is the real part of the second number, y1 is the real part of the first number, y2 is the y1 is the imaginary part of the first number, y2 is the imaginary part of the second number, right? So what if I add these two numbers? So z1 plus z2, you know complex number addition, right? So this is going to be x1 plus x2 plus j y1 plus y2. So what is the real part of the whole thing? What is the real part of z1 plus z2? That's going to be x1 plus x2. But what is x1? x1 is the real part of z1. x1 is the real part of z1. And what is x2? That's the real part of z2, right? So with that said, I can now say that this is very simple, right? Real part of z1 plus z2 is the individual sum of the real parts. So real z1 plus real z2, real part of z2, right? That's understood, right? So now I can copy this, write it down, and I can now change the condition from real part of a plus s greater than 0 to something like the real part of a plus real part of s, this whole thing to be greater than 0. All right, and similarly this is negative, and I'm just calling it otherwise, when the real part is negative, right? Sum of the real parts is negative, so I can say that, right? So this was real part of a plus s, I can say that, right? Now of course this can be actually further simplified to, I can bring one of them to the right hand side. So with that said, I can say 0. So right, yeah, 0 if I can say the real part of s, which is again sigma. So I can bring this one to the right hand side and say greater than minus real part of A, and this is undefined otherwise. Okay, so what did we just say? We say that this limit will be 0 if this condition is satisfied. So this is the condition: real part of S will have to be greater than the negative value of the real part of A. So if A is a complex number, then like that. So with that said, let's go back to the definition here. Okay, let's go back to the definition. So we are saying that this is minus 1 by A plus S, and of course the limit is, we are putting the limit to be equal to 0, but the moment we do that, we are assuming something. The moment we are putting the limit to be 0, we are assuming that the real part of S is greater than minus real part of A. We are assuming that. Of course, if A is a real number, then of course we can just say real part of S, which is sigma, is greater than A. That's a minus 1 here. And of course I am running out of space. Just a moment. Okay, so and with that said, I can say this is 1 by A plus S, right? The answer is 1 by A plus S, but there is just one condition. Okay, the condition is assuming that the real part of S is greater than minus real part of A. Otherwise this will not converge and we won't even have a Laplace transform. So again, the same thing, the Laplace transform of e to the power minus at, Laplace transform of e to the power minus at into ut, so is this one, 1 by A plus S, but under this condition. If this condition is somehow violated, then we won't have the Laplace transform converge, right? Okay, got it? So with that said, we have this discussion there, right? And of course with that said, I would have a non-causal answer for this. Okay, so if I now ask you what is the inverse Laplace transform of 1 by A plus S, okay, the causal answer is e to the power minus at ut. Okay, of course there will be a non-causal answer. So your kind of a partial homework, I'm not writing it as the homework, but your for your brainstorming, you can try to figure out what is that non-causal signal for which the Laplace transform is this one, but the condition is the other way around. The condition for that would be real part of S less than minus real part of A, with the same Laplace transform as the result. Try figuring the function out for which that happens, because there will be another function for which this happens. So only the ROC will be different, the region of convergence will be different. So a few examples. So what number one example? So for example, if I say what is the Laplace transform of e to the power minus 2t, minus 2t ut. Thankfully this signal would also have a Fourier transform. So let's just say instead, what is the Fourier transform of e to the power minus 2t ut? You did this in our earlier semester, and of course the answer would be this, because this is a real number and real and positive number, and subsequently I would have this. Question is, what is the Laplace transform? E to the power minus 2t ut. That's 1 by S plus 2, because the answer is 1 by S plus A, right? So 1 by S plus 2, just like that. All right. Now question, what is the Fourier transform of e to the power positive 2t ut? That is, this one would be undefined, because this signal is not absolutely integrable, and as such this won't have a Fourier transform. And for this one, What about the Laplace transform of e to the power minus e to the power 2t ut? The answer is 1 by s minus 2, right? Right? Because we just have learned that Laplace transform e to the power minus at ut is 1 by s plus a. But of course, there are certain conditions that we are kind of not writing here, right? There are certain conditions that we are not writing here. So, I mean, this is true, right? This is true, but under a condition, right? This is true under a condition. What is the condition? What is the condition? The condition is that the real part of S, which is sigma, should be greater than minus the real part of A. So real part of A. But what is A here? A is 2. So basically A is equal to 2, right? So A is 2 here. So that is real part of S, which is sigma, should be greater than minus 2. That's the condition here. So the region of convergence here is this one. Okay. So sigma should be greater than minus 2. So look very carefully. Sigma should be greater than minus 2. Unless you choose sigma to be greater than minus 2, this Laplace transform won't converge. Okay. Similarly, this Laplace transform won't converge. You can check the condition. This Laplace transform won't converge. So of course the condition behind this is that the real part of S should be greater than negative real part of A, and here A is minus 2. In this example, A is minus 2, of course. So of course subsequently this can be written as real part of S, okay, real part of S to be greater than minus of minus 2. So that's plus 2. So real part of S should be greater than plus 2. Alright. And of course the Fourier transform does not exist for this. Okay. Got it? Alright. So if you have any query, feel free to ask at this point. And subsequently, you can just use it as a corollary. So you can say, what is the Laplace transform of e to the power 0t into ut? So Laplace transform of just ut, right? So that is going to be 1 by s plus 0, of course. And the condition being, so here a is equal to 0, right? And the condition would be real part of s should be greater than minus real part of A, but since A is 0, this is 0. Again, this is something we proved, right? Alright. Feel free to ask any question that you might have at this point. So the very thing you need to take away from this is that Laplace transforms would come bundled with something called the region of convergence. Region of convergence will come bundled with region of convergence, right? Now, one very important point to note. Ask away any question that you might have. Is that the systems and the signals we are going to talk about in this course are causal, right? Thus, I said this earlier, thus GT would be causal. GT would be causal. GT is the impulse response of the system, would be causal. XT would be causal, and YT would also be causal, which means GT would be equal to 0 if t is less than 0. XT, that is the input, that is also going to be 0 if t is less than 0, and also the output of the system YT, that's also going to be 0 if t is less than 0, right? So impulse response would be causal, the input is also considered to be causal, and if the impulse response of a system is causal and the input is causal, the output has to be causal. So under all those scenarios, if I take any of these and calculate the Laplace transform, okay, so if I take any of these causal signals and calculate their Laplace transform, we essentially have something like this. So we essentially have the Laplace transform of, say, something like xt. By the definition, it's going to be from minus infinity to infinity xt e to the power minus st dt. So that's again defined as the bilateral Laplace transform. Right? But this can be split into two limits for negative values of t and positive values of t. So from minus infinity to 0, xt e to the power minus st dt plus 0 to infinity xt e to the power minus st dt. Now, if my signals are causal, then this is going to be 0, right? This is going to be 0. This is going to be 0 since my signals are causal, right? Since xt is causal. For a causal signal, the value of the signal is 0 when t is negative. So essentially, this turns out to be integration from 0 to infinity on xt e to the power minus st dt. Right. All right. Right. So essentially, this turns out to be the thing that we actually calculate, right? So what did we start calculating? We start calculating the Laplace transform of xt, and instead of calculating the limit from minus infinity to plus infinity, if the signal itself is causal, then we have something like this. This is for only the positive values of t, because for negative values of t, the result is 0. This definition is known as the unilateral Laplace transform. So unilateral Laplace transform. And if you look through any book on signals and systems, they usually they do talk about bilateral Laplace transform, right? All these. But if you look at any book on control systems, they do talk about unilateral Laplace transform, because they do inherently assume causality of the signals, and that is why they do neither talk about the region of convergence, because they consider everything to be causal, so you would only have one possible answer, okay? And they do not even talk about bilateral Laplace transform, because why talk about bilateral Laplace transforms? Because when we only talk about causal signals, right? So if you are only talking about causal signals, then we do not have to talk about bilateral Laplace transforms. And again, if you are only talking about causal signals, we don't also have to talk about the region of convergence, because by default there will be only one possible answer, right? So that is why for the most part in this course we are going to talk about unilateral Laplace transform, right? But while deriving certain formula for the Laplace transform, certain properties of Laplace transform, we are going to use the bilateral definition, all right? Because that is how the Laplace transform is defined in a bilateral way. But for the most calculation, we are going to use unilateral Laplace transform. And also doing bilateral Laplace transform is more or less difficult. And that is why if you use any Python, any software based tools, so right, so and because of these reasons, okay, all popular software for calculating Laplace transform would only consider unilateral Laplace transform, because that is the most used scenario. Like 95% of the scenarios that we use Laplace transform for are unilateral in nature. And these tools that I am talking about, they include Python with SymPy, of course. They include MATLAB. These tools include Mathematica. So all these tools actually, all of them considered unilateral Laplace transform, simply because who on earth use Laplace transform? Mostly control system engineers. And what kind of signals do they deal with? Causal signals. And the answer is plain and simple, right? And even also along with that, I mean, implementing bilateral Laplace transform using a computer program is way more difficult than implementing unilateral Laplace transform. I mean, all the convergence and criteria, I mean, they become very difficult quickly. So people try to get away with the simplest possible result here. So with that said, we are going to end the discussion here, but not without talking about how we actually can calculate the Laplace transform of signals using Python, right? So wait for a second. Let me start a Google Colab session. So if you have any query, feel free to ask. All right. So let's go to the screen here. Again, if you have any query, feel free to ask. I'm showing you how to actually do this. And using Python, right? All right. The package you need to import is SymPy. Okay. So for this, you need to import. So I'm showing you the proper way. Earlier, I know that earlier I have shown you how to do the Laplace transform in kind of an improper way. So right now I'm showing you how to do this in a proper way. Okay. Import SymPy as some symbolic name, right? This is, again, you are familiar with this. This is kind of the nickname of the model, the package, right? You can call it anything you want. I'm just calling it SY. Okay. Just import SymPy, because we are going to do certain symbolic computations. So we are learning how to do Laplace transforms using a computer program, right? So Python, right? So if you have Jupyter, if you have Anaconda distribution installed in your computer, you can do it in your own computer. Otherwise, you can just go to Google Colab and launch this one. All right. So now the first thing you need to do is to create variables. Let Python know that I'm going to treat S and T as symbols, not just as symbolic variables, not just numerical variables, right? So it won't hold numbers or arrays or lists, some other Python objects. They would be symbolic objects, right? So here is the syntax. Okay. So I'm calling S and T and I want them to be Python symbols. So I would call them sy vars, and I'll say s and t. Again, this is just a syntax that came along with SymPy. Okay. Oh, sorry, SymPy, not vars. Okay, SymPy dot var. Sorry. All right. So now we have defined s and t as symbolic variables. If I just say whose at this point, you would see s is a symbol. What is s? Is a symbol. What is t? T is also a symbol. I do not want them to be variables of other kind, right? So this should be symbols. Keep that in mind. Okay. All right. So with that said, now I can calculate the Laplace transform. How can I calculate the Laplace transform? Again, Laplace transform function also comes from SymPy package. So from SymPy package, I am calling the Laplace transform function. So sy, so SymPy dot Laplace transform. So from within Laplace SymPy, I am calling the Laplace transform function, and I'm going to pass in the function for which I'm going to calculate the Laplace transform. Say this is going to be, say for example, say Laplace transform of, what should I calculate? So e to the power minus 2t. Okay, and I don't have to write ut. Keep in mind that SymPy also calculates, considers everything to be unilateral, right? So the signals are by default assumed to be causal, right? And of course, I'm considering starting from t and going up to s. And these help menus are wreaking havoc. Okay, and now it says exponential is not defined because I did not call the exponential function from the SymPy library. So I have to call the exponential function from the SymPy library. So it now says the answer is 1 by s plus 2, and then it shows certain conditions, 0, true, and these kind of conditions. I'm not going to talk about those. So I'm going to just kind of try to hide those conditions. So I would say no const equal to true. So answer is 1 by s plus 2. And while I'm at it, let me just do one more thing. Again, you will be given this notebook, so you can actually write along with this notebook, on this notebook. So the answer is 1 by s plus 2. Can you see the answer? This is pretty tiny here, but it is properly rendered in a sense, right? The answer is 1 by s plus 2. And if I did it in my own computer, it would look even better. All right. So, all right. Fine. So, what if I want to take the Laplace transform of, say, what if I want to take the Laplace transform of e to the power minus at? I'm not writing ut once again, simply because you have to understand the fact that it is unilateral. So ut won't make any difference, right? Now it says a is not defined. Now I'm treating a as a symbolic variable. So a is not defined. So I have to define a alongside this one. So how do I define a in addition to this? I could have considered writing this as this. So that would do it. So if I say this, then a would be treated as a symbolic variable like that. Let's do that. So that way I have a here. Now if I run this now once again, now answer is 1 by s plus a. Is it visible in your computer? Right? I think it's visible, right? So this is 1 by a plus s. So the answer is 1 by a plus s. Pretty happy answer, I think. All right. So now let's mess things up. So what if you want to just do Laplace transform and forget about everything else, right? So with that said, what I usually do while working like this, I do not import SymPy as .sy and calculate it the proper Pythonic way. What I do, I just mess things up. I simply import everything from SymPy, and then I do import SymPy.abc. From SymPy. What am I saying? I'm saying from SymPy import everything. from SymPy import everything, and again from SymPy.abc import everything as well. So that way what I have done, I have just imported everything that is there in SymPy and imported everything that is there in SymPy.abc. What is ABC? Is the variable list. So now every variable that I use right now would be a symbolic variable. So I don't have to write this. So I showed you the proper Pythonic way, and then I'm showing you the proper engineering way of dealing with things, right? So now I do not have to say SymPy dot Laplace transform and everything. I just can say Laplace transform. I do not have to say SymPy and these, and I don't even have to worry about variables. This works. This is s plus 2, right? And I do not have to say this. I don't have to worry about this. Again, all the variables are predefined for me. So this is s plus a. Okay. So let's calculate the Laplace transform. So Laplace transform something like, say, t into, say, sine t. So what about Laplace transform sine t? We are going to talk about those things in the next class. Sine t, starting from t, I'm going to, so t is the actual variable, time domain variable, s is the frequency domain variable, and the answer is 1 by s square plus 1. These are the things you should be familiar with. Okay, so I can now copy this. So question, what is the Laplace transform of t sine t, say? And we are going to learn how to actually calculate all these things. So this is 2s by s square plus 1 whole square. All right, fine. What is the Laplace transform of t square? So this is t square into e to the power minus at, t square e to the power minus at into sine omega t. So you're calculating the Laplace transform of t square into e to the power minus at into sine omega t. Let's calculate that. The answer is this. This mess is the answer. Alright. So as you can see, you can very quickly calculate the Laplace transform, and that's not just it. You can also calculate inverse Laplace transform pretty easily. Okay. Name of the function is inverse Laplace. I just said inverse, and see how many different transforms there are. Okay, there is cosine transform, Fourier transform, Hankel transform, Mellin transform, sine transform, and Laplace transform. And cosine transform, sine transform, they are parts of Fourier transform, but forget that. So in addition to Laplace transform, we have Fourier transform, Hankel transform, and Mellin transform. These are pretty popular integral transforms. So these transforms, they fall under the category of integral transforms. These are those. So I'm saying inverse Laplace transform, and they have their particular utilities. So let's calculate the inverse Laplace transform of 1 by, say, s plus 3, say 1 by s plus 3, and of course the variable is now from s to t, right? So first I'm writing the frequency domain variable and then the time domain variable here. So well, right? This is very simple. When I'm doing the Laplace transform, I am writing t first and then s, indicating that I'm jumping from time domain to frequency domain, and here it indicates that I'm starting from frequency domain and going to time domain. And look at the answer. The inverse Laplace transform of 1 by s plus 3 is e to the power minus 3 into theta t. What is theta t? It's ut, right? Theta t is the Heaviside theta function. What is Heaviside theta function? Heaviside theta function is the unit step function. So right, it's just like that. So I could have just said 1 by s plus a, and now it has given me a very complicated answer that looks pretty complicated, that is written as real part of a and such, right? This is to make sure that the answer is consistent, answer is proper, because it is considering a to be a complex number. So I can say this, that would be fine. But if I just write a, it would treat a as a complex number and it will show the answer subsequently like that. All right. So again, if you have any query, feel free to ask at this point. Otherwise, we are going to end the discussion. And not just this, I mean, you can do pretty silly things, right? You can make up complicated things. So maybe there is a cube here, and there is s square here, who knows. Let's do the Laplace transform of this, inverse Laplace transform of this. All right, so I have this as the inverse Laplace transform. Again, theta t is ut. Okay, that's the Heaviside theta function. All right, I think that will be the end of today's discussion. So we have learned how Laplace transform is different from Fourier transform, and we have kind of figured out the convergence criteria, and then we saw that it is not always necessary to write down the convergence criteria if we are talking about causal signals. All right, and also for causal signals we do not have to show the region of convergence, as well as we can only deal with unilateral Laplace transforms, right? So with that said, that's the end of today's discussion. If you have any question later on, feel free to ask them, drop me an email, and I shall share this with you. I shall share the file, share the Google Colab file, as well as today's handouts with you. It will be, let me just share this file a moment. All right, so that's the Google Colab link here. All right, so